So let's start by talking about entropy and coding and how we can use bits to represent items from a set or items coming from a source that might be generating, say, text. Okay, so let's start with a basic question where we have a set. In this case, we've got the set of playing cards, 52 cards, and we'd like to identify those items using codes. We'd like to come up with binary 0-1 type codes for referring to these cards. Well, let's first just find a way to assign numbers to each of these cards. And so maybe one way to do this is we have these 4 ranks and we have these 4 suits and we have 13 ranks per suit. So let's just say that our code is equal to the suit where we've encoded the suit somehow, like maybe with the numbers 0, 1, 2, 3, times 13, that should be a times 13, plus the rank. And that's assuming that the ranks, so like where the ranks vary from, let's say, ace is 0, 2 is 1, 3 is 2, ... up to king is 12. And then the suits, obviously we need some way of giving 0, 1, 2, and 3 to the suits. So you get the idea. So here we go. So let's say our code is rank plus 13 times the suit. And here's our scheme for the suits. Spades are 0, hearts are 1, diamonds are 2, clubs are 3. Okay? So what binary code would we give to each of the cards if this is our strategy? Okay, so I want to fill in what binary code I would give to each of these. Okay, well here's the ace of spades first at the top. So for ace of spades, the suit is 0 and the rank is 0. So we get 0 plus 13 times 0. We can write in 0 for ace of spades. 2 of spades, now the rank is 1 higher. So we're going to write 1. Now 3 of spades, rank is 1 higher. So we're going to write 2, but we're going to write 2 in binary. So that's 1, 0. 4 of spades, 1 higher, and so on. Now let's go down. We've skipped to the end, right? The king of clubs is actually the highest of all the cards in our coding scheme. So that one is going to get code that in decimal would be 51. And then this would be 50, this would be 49, this would be 48. 48 is easy to write in binary, relatively, because it's 32 plus 16. So let's go ahead and write that. 32, 16, 8, 4, 2, 1. Okay, so that's the binary version of 48. So now the rest are easy because we just keep going up by 1. Great. And there's my binary codes for all of the cards in the deck. So how many bits did I need to refer to cards in the deck? Well, the way I've drawn it here, it's suggestive that I didn't actually necessarily need to use the maximum number of bits for every card. But the maximum number of bits that I did need, as once I counted all the way up to the king of clubs, was 6. Okay? So how many bits in general are required to encode items from a universe U? Well, it's going to be the log base 2 of the size of that universe and then round it up. And if we just write down log base 2 of the size of the universe, this corresponds to an idea called the worst case entropy of a set. The worst case entropy of a set is the log base 2 of the size of the set. Okay? And what this says about the code words is that if the codes all have to be the same length, right, then they have to be then the length you should pick would be this, but rounded up to the nearest integer. Okay? So if all the codes have to have the same length, they should be this rounded up. In the case of the playing cards, that would be 6. If the codes are allowed to have various lengths, then what the worst case entropy is telling us is how long the longest code must be at least as long as the worst case entropy. So we can also, again, think back to the playing card example, because actually our codes had various lengths. You know, our code for the ace of spades and the 2 of spades were both just one binary digit. but the longest codes were still 6 bits, right? So it still adhered to this principle that the longest code has to be greater than or equal to the log base 2 of the size of the set. Okay, and this notion is called the worst case entropy. When we talk about the worst case entropy, we use this WC subscript here. Okay, so that's our first sort of concept of entropy. And so let's just apply this in a few situations. So, okay, let's use the concept of worst case entropy to write down how many bits are going to be required to identify an item from each of these sets. You know, let's say we're using codes that all have the same length. So what would be a good length I could pick if I had to distinguish heads from tails? Well, that's easy. It's just 1 bit, right? Heads or tails. How about a roll of a die? Well, it's not 1 bit. That's not enough. It's not 2 bits either. That's not enough. I can only distinguish 4 things with 2 bits. So it's going to be 3 bits. I can distinguish up to 8 things. So I can distinguish 6 different rolls of a die. And now I've got a picture of a roulette wheel. I guess different versions of the roulette wheel have different numbers of slots, but it has either 37 or 38 slots. So that, just like with the playing cards, is going to end up being 6 bits, right? Log base 2 of 64 is 6, so 64 is plenty. 6 bits is plenty to refer to 37 or 38 things. Okay, and so this is our notion of the so-called worst case entropy. So here's a quiz question. Let's see. If the size of the universe is 2 to the n, if the size of the set that we're actually trying to encode is 2 to the n, then what is the worst case entropy? Well, it's just the log base 2 of the size of the set. The size of the set is 2 to the n, so that's just n, right? Let's say now that the universe is the set of all length n strings from a certain alphabet sigma, where sigma has small sigma different symbols in it. So there's an alphabet big sigma, it's got symbols in it, and we'll call them 1, 2, 3 up to little sigma. Okay, so what's the worst case entropy of this set? Well, I need to write h sub wc of this universe equals log base 2 of, okay, so I've got a choice of sigma things at each position, and I've got n positions. So I'm going to write it like that, and then because this is a log, I can bring the n down in front, and log base 2 of sigma. Okay, so just a couple of examples of applying worst case entropy. Okay, but we have this question of how do we pick the code words? And we've already found that there's one choice that we have flexibility on, which is we can pick codes that are all the same length, or we can pick codes that are various lengths. An example of a code where we've used various lengths, it would be Morse code. So if you're familiar with Morse code, this is the kind of code that you'll sometimes see, in movies where people are communicating like via telegraph or submarine or something like that, and they're tapping messages, and the messages are going beep, 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 beep. And they're using a code that consists of 2 different kinds of sounds, a brief sound that's sometimes called a dit, and a longer sound that's sometimes called a da, or it's also called dots and dashes. And these are the different codes here, where the little circles represent the short sounds and the longer bars represent the longer sounds. And you can see that a design choice has been made here, which is that for some of the more common letters that you might have to type out, like E, or the other vowels, they're relatively short. Let's take a look. Oh, look, T is also very short. Why is that? Well, that's because these are the more common letters, right? So a design decision has been made that the more frequently used letters should receive shorter code words that take less time to tap out on the telegraph machine. Okay, makes perfect sense. So if the codes can vary in length, we can use shorter codes for the more frequent events. And in designing this set of codes that can be variable lengths, what we're seeking to basically minimize is something like the average or the expected length of a code that we would have to generate. Okay, so in other words, we're thinking of the source as being something that's generating, let's say, English words, reasonably common English words, and we have a model for reasonably common English words and about the characters that tend to be in them. And what we're saying is, under that model, we want the expected code length to be short. Okay? And so we can write out expected code length. This is this L bar. L bar equals the probability, what equals this sum over all possible items from the universe, all possible letters we might want to convey, of the probability of that letter under some model times the length of the code word that we use to encode that letter. Okay. Right, so L of U is the length of the code for U. I should just say briefly, Morse code has there's another principle at work here, which is that the space between words and the space between letters are both delimited with pauses. So that's not shown here, but there's a pause between letters and a pause between words. Okay, so let's say instead of thinking of what we have here, we're already starting to think in terms of not so much a set as a random source that has a different probability of generating different letters from the alphabet. So instead of thinking of items small u from a universe big U, let's think of a discrete random variable, x, and say that its sample space, and think in terms of its sample space, omega, and a probability function. Okay? And then let's, again, write down something that looks a bit like entropy. And now we want to write down something like the entropy of this random variable. The entropy is going to tell us something about how long, on average, we expect a code word to be. How long on average. Now let's write down a concept of the entropy of this random variable. And this entropy is, roughly speaking, going to correspond to how long do we expect a code for something from this, generated from this random variable to be. Okay, so let's look at this equation. We've got the sum over everything from the sample space omega, each item in the sample space, of the probability of that item times log base 2 of 1 over the probability of that item. Okay, we can actually rewrite this a little bit. So if we consider, this piece right here, this could also be written as probability of s to the minus 1, and then the log makes that minus 1 come down, and the minus 1 indeed can travel all the way to in front of the sigma. So we get this form here, which is another way of writing down what's called the Shannon entropy of the random variable x. Okay, so this, we've already written down the worst case entropy. That was h with a subscript of WC. Now we've got h with no subscript. That's typically how we write the Shannon entropy of a random variable, which has this as its definition. Okay. All right, so let's look at some random variables, because we want to get an impression of, is this something that maybe, as we would expect, gets higher, as it seems like we maybe need more bits. We need to spend more space in order to create the codes for items that come from that source. So let's just see if that sort of seems to be true. So let's look at the first example where we've got very simple random variable. It's just a coin flip. It's a fair coin flip. So the probability of both outcomes is exactly 0.5. Okay, so I want to write down the Shannon entropy of this random variable. So I've got to do probability. So I've got to do probability of the first outcome, which I'll do heads first, times log base 2 of 1 over that probability, plus, now let's do tails, again 0.5, and again log base 2 of 1 over that probability. So what do I have here? I have 0.5 times the log base 2 of 2. right? So that's 1 plus 0.5 times log base 2 of 2. So that's 1. Whole thing equals 1. Okay? So the Shannon entropy of that fair coin random variable is 1. Now let's make it an unfair coin. So we're getting somewhat closer to the situation of modeling English letters, where some letters are more likely than others. Let's make the coin unfair. All right. This one, the math is a little harder to do off the top of your head, but I've got it all written down so I can do it. Log base 2. This now is heads. Probability of heads is 0.9. Do times log base 2 of 1 over. So I've got probability of heads, which is 0. So I've got probability. So I'll start with probability of heads, which is 0.9, times log base 2 of 1 over 0.9. And we do the same for tails, 0.1 times log base 2, 1 over 0.1. What do we get? 0.9 times, this is around 0.15, that log. 0.1 times, that's around 3.32, that log. This ends up being about 0.47. Okay? Okay, so the entropy is lower. The Shannon entropy of this random variable that had a more lopsided probability function, 0.9 loaded with 0.9 for heads and 0.1 for tails, this more lopsided probability distribution yielded a lower Shannon entropy. Okay, kind of makes sense. If it's more predictable what the outcome of the random variable experiment is going to be, we shouldn't need as many bits to write down the answer, right? We can sort of specialize. We can say we're going to give a short code word to the more likely answer, and most of the time we'll be right. We'll be able to use the short code word. Okay, so let's visualize not just the 2 points that we just discovered. All right, so like here's our coin flip random variable, but I'm letting the probability of heads now be the variable p. I'm going to vary p along the horizontal axis. I'm going to plot what is the Shannon entropy of a random variable, random coin flip variable, Bernoulli random variable, that has that p on the vertical axis. So we know 2 points because we did 0.5. 0.5 had a Shannon entropy of 1. So there's that point. And we did the point p equals 0.9, which had a Shannon entropy of around 0.47, I think we said. So there's that point. And so now let's draw the rest of them. All right, this is now, I just tried a bunch of values of p ranging from 0 up to 1. And there we go. We've got a Shannon entropy curve, and it peaks at p equals 0.5, and then it goes down symmetrically on the other side. All right, so let's look at a few other examples of Shannon entropy and try to get used to this idea of what kind of lopsidedness leads to higher or lower Shannon entropy. So let's move away from coins. Let's talk about die rolls. So let's say we have a die roll random variable, fair die. So the probability of 1, 2, 3, 4, 5, or 6 are all 1/6. So I can write down what's the Shannon entropy. It'll be a little more convenient for me to write it as a sum this time. Sum from I equals 1 to 6 of 1/6, probability of that roll, times log base 2 of 1 over 1/6, which is 6. Okay, what does this end up being? Well, I'm just adding up 1/6 log base 2 of 6 times. So those add up to log base 2 of 6. And that's around 2.58. Okay, so that's the Shannon entropy for the die roll. And now let me show you 5 different possibilities for what the probability distribution of the die roll could have been. Obviously, this is the one we just examined, but then here's a very dramatic one. Here's one where one outcome is certain, and the other are certainly not going to happen. Here's one that mimics the coin flip. And then here are 2 others that are kind of in between. They're in between in different ways. Okay, and each of these 5 possible probability functions, probability mass functions for this die roll corresponds to one of these points over here. So do we know which is which? Okay. Well, which do you think is the highest one? Well, it's got to be this one, right? This is the one with the most surprise, right? There's the least lopsidedness. So this must be the blue one. So I'm going to say this is the blue one. And then which is the one with the least surprise? Okay, well that's definitely this one, right? The outcome is a foregone conclusion. So that's that one. Okay. Now how about this one? Well, we already know the Shannon entropy of that one. That's the same as the fair coin Shannon entropy, because that basically is a fair coin. There's 2 different faces that have equal probability, and the rest have probability 0. That's the same as a coin. So that must be the one at 1. Right? So that must be that one. Okay. Now, which is which with red and green? That's a little harder. I don't know about you, but I think I would probably just have to do the math to figure that out. So I'll just tell you. The red one was the slightly higher entropy one, and the green one was the slightly lower entropy one. But there we go. That's the Shannon entropies of these 5 different versions of a die rolling random variable. Okay. There's something familiar going on when all the outcomes are equally probable, right? Which is that we're taking a sum of a log that ends up just being the log. And since it ends up just being the log, it should remind us of something. It should remind us of the worst case entropy. So let's just see what I mean here. So let's say we're taking the Shannon entropy of a random variable x that has a sample space omega. And so what's that Shannon entropy sum going to look like? Well, let's write it. It's the sum over all possible items from omega of the probability of that item times the log base 2 of 1 over probability of that item. Okay, and if we think of, since they're equally probable, we know what the probability of any given item is. It's just 1 over the size of the sample space. It's 1 over the size of big omega. So let's substitute that in. So this is 1 over size of omega times log base 2 of 1 over size of omega, so that's just size of omega. And then we're in the same situation we were in when we were adding up all the 1/6 for the fair die roll. This sum now basically just turns into this part here. So we just have log base 2 of size of omega, which is the worst case entropy of omega. Okay? So when the outcomes are equally probable, the Shannon entropy of the random variable is nothing but the worst case entropy of its sample space. Okay? Let's just review here. We've talked about Shannon entropy, h of x, which is a function of a random variable. And that random variable, well, that could be modeling some kind of data source. Like if we're dealing with text, we could think of the random variable x as being a generator for text. If we're dealing with something else like somebody speech, then big X is generating bits of speech. And we're assuming, though, that this source is memoryless. In other words, every time we go to get the next letter, every time we go to get the next utterance, or whatever it is, from our random variable x, it's a new independent draw from that random variable. Okay, it's a new independent and identically distributed draw each time. So this is a not very sophisticated model, and we'll come back to this. We'll try to look at models as well that consider that the letter or the utterance at one point in time probably depends on the previous. We'll deal with those later. For now, we're dealing with memoryless sources. So far we've seen this notion of worst case entropy, which is defined, which is a function of a set. And we've seen the notion of Shannon entropy, which is a function of a random variable. And we see this connection, which is that when all the outcomes for the random variable are equally probable, then the Shannon entropy equals the worst case entropy of its sample space. So now we're going to add a third notion of entropy, which is a notion that we can use when we don't necessarily have a model for how frequently things occur, but we do have some data. We have an example of a string, okay, that's been emitted. So let's say we have some memoryless binary source. Just for simplicity, we'll stick with binary. We'll just stick with a source that's emitting zeros and ones. But we also have an example string that it's emitted, which I'll call B. And we're going to think of a new notion of entropy, which is called the zero-order empirical entropy, which is a function of that string. And essentially what we'll do is we'll count the zeros and ones in the binary string B, and then we can use them to form our best guess as to what the random variable was, as to what the memoryless source was that generated the random bits, that generated the bits in this example string. Okay, so if we have, if we know the number of ones in our output string, and n is the length of the output string, b, then we want to write down basically how can we think of the zero-order empirical entropy of the string b as the Shannon entropy of a random variable. All right, so let's just write Shannon entropy of, and now this is a, we're in basically a loaded coin flipping regime here, right? So if we have observed the bit string and we see that it has, let's say, 90% ones, then it sounds like what's been happening is we've been flipping a loaded coin with 90% chance of heads or 90% chance of 1, 10% chance of 0. So in other words, we can form a fraction, the fraction m over n, and the fraction m over n tells us the probability of a 1 being generated by this random variable. In other words, we're taking the Shannon entropy of some random variable x, which we'll say is distributed as Bernoulli m over n. Okay, so the zero-order empirical entropy of the bit string will be the same thing as the Shannon entropy of a Bernoulli random variable that has m over n as its probability of generating a 1, its success probability. And so what is the Shannon entropy of that distribution? Well, we'll just go back to definition of Shannon entropy. Let's start with the outcome that it emits a 1. That happens with probability m over n times log base 2 of 1 over that probability, so n over m, plus, now let's go with probability of 0. This could be n minus m over n times log base 2 of 1 over that, so n over n minus m. Okay? All right, so this h sub 0 of b, which we wrote out here, is the same thing as the Shannon entropy of a Bernoulli random variable, where the p parameter of that Bernoulli random variable equals the fraction of ones in that binary output string. And of course, we can generalize this beyond binary, right? It doesn't have to be binary, but that made this a nice simple example where we could say the random variable was Bernoulli. But you can imagine the random variable is some multinomial random variable, and then you can talk about a whole alphabet. So, just reviewing, because we've now seen 3 different notions of entropy, and I want to make sure we can keep them sort of straight, is we've seen the worst case entropy, H sub WC, which is a function of a set. We've seen the Shannon entropy H, which is a function of a random variable. And we've seen the empirical zero-order entropy, which is a function of a string, of a sequence that was emitted by some hypothetical random variable. Okay, I used B because I did a bit string, but it doesn't have to be a bit string. It could just be any sequence. Okay, so we've talked a lot about notions of entropy, and these notions of entropy will sort of help us figure out how long should our codes be for encoding different symbols. But what should the codes be? We haven't answered the design question of how do we actually design, say, a function that goes from symbols in the original alphabet to good codes for those symbols. All right, so what do we want out of a good code? We've already said we want to minimize the average code length, which is to say we want the average code length to approach the zero order empirical entropy of the string that we're trying to encode. We would like the code to be unambiguous in the sense that each possible string gets a distinct encoding, a unique encoding. We can't confuse 2 different strings. 2 different strings can't have the same encoding. And we'd like to be able to do this efficiently, both encoding and decoding. And we'll see a little bit more about what we mean by efficiently in a moment. Okay, so we already said that when we wrote down the Shannon entropy, it looked like this, right? It was the probability of the item from the sample space times log base 2 of 1 over the probability. And this is sort of a hint here that this is probably something like how many bits we're going to use to encode that item, that symbol from the alphabet, or that item from the sample space. Okay? So the Shannon entropy equation itself gives us a hint that perhaps we would like to have codes of that length, right? So that as a way of optimizing the average code length. So let's think about what would be a function that could give us a code like that. So a bit of setup. Let's say, again, we have a source that's emitting symbols from an alphabet. Let's use a DNA alphabet for this example. And the source is memoryless. And we've gone ahead and, let's say, somebody has given us a model, or we've counted up the numbers of A, C's, and G's, and T's in a particular string, and that gave us this model. But we have this model for what's the emission frequency for, what's the probability of A, probability of C, probability of G, probability of T. Okay, those probabilities add to 1. And there's a function C. This function is the one we're designing, right? We would like to design a function C that maps symbols, A, C, G, and T, to binary code sequences, right? So it goes from a letter from the alphabet, A, C, G, or T, to 0, 1 star, star being any number of zeros and ones, right? As a string consisting of a concatenation of some number of zeros and ones. What kind of C do we want? What do we want C to do? Well, let's think about this in terms of a couple of concrete proposals for what C might do. And hat tip to these great YouTube videos where I got the next couple of examples that I'm going to show. Okay, so proposal 1 is this. Here's one set of codes. So my code for A is 0, code for C is 1, 0, code for G is 1, 1, 0, code for T is 1, 1, 1. Obviously, these are variable length codes, right? I used a shorter code for A. Stands to reason because A is the most frequent out of all the symbols in the alphabet. Okay, so if that's my proposed function C, a question that I can ask is, does every symbol, A, C, G, and T, get a different code? right? And obviously yes, right? These are all different. Okay, so far so good. C is injective. Each of the inputs gets a distinct output. Okay, now just as a to take the example a bit farther, let's actually encode a string. So here I've got this string AAGC. I should use my function C to write down what would be the code that I would get if I encoded each character and concatenated the codes. Okay, so my code for A is 0. So I'll put a 0 down here. And my code for A again is 0 again. So I'll put a 0 down there. I'll match the colors. My code for G is 110. So now let me put 110. And my code for C is 10. So I'll put 10. Okay. Great. There's my code. And so obviously I can encode, right? It's a simple process to encode my string. But a question is, can I get back the original string once I've encoded it with this set of codes? So here's a new encoding. This is a new bit string. It's the bit string that corresponds to the encoding for some input string. Can I get back the original input string? Okay, so let's think through this. All right, well, let's go left to right, and let's see. Let's see, I've got 1. My very first bit is 1. So I could be looking at the beginning of the code for C, 10, or the beginning of the code for G, 110, or the beginning of the code for T, 111. I don't know yet, so I have to keep going. All right, what's the next bit? It's 1. Okay, all right. So let's see. None of my codes are 1, 1, but 2 of them start with 1, 1. So it's sort of down to these two. It's either G or T. All right, so I'll keep going. So I go to the third bit, and it's 1. Okay, got it. Those first 3 bits must be the code for T. Note that there's no ambiguity here, right? I know if I see 1, 1, 1 here at the beginning, it can't, there's no G, C, or A here, right? Because there's no zeros here. So that we know there's no A, C, or G. It has to be T. So I can start to decode by writing a T up here. Okay, and those 3 became a T. Now I'll keep going. I see a 0 next. Okay, well 0 is a code. That's the code for A. Okay, so I know the next character is A. Okay, I get to the next one. 0 again, so A again. So I know the next character is A. Let's keep going. Okay, now I've got a 1, so again I've got my choice. It could be G, C, G, or T. And the next one is 0, so okay, so I know it's C. All right, so C. Right? So can I recover the original string from the code? Yes. So at least in that example, I could do that. There was no ambiguity. Okay, let's pick a new code, not this one. Here's a new code. All right. So I've got the code for A is 0, code for C is 1, code for G is 0, 1, code for T is 1, 0. Does the function C still give a distinct code for each symbol in the alphabet? Yes. Again, it does have that property. Now let's keep looking at it. Let's see if we can use it to encode this string. Okay, code for A is 0, code for A is 0, code for G is 0, 1, and code for C is 1. 1. All right, great. So I could encode. Now the question is, given this string, this is the same string that I just generated by encoding AAGC, can I decode it unambiguously? Well, let's think about that for a moment. So I've got a 0 here. Okay, well, as I look at my codes, there's 2 of them that start with 0. One of them is just 0, and the other one is 0, 1. I kind of don't know which one it is yet, so I have to keep going. Okay, I've got 0 next, so the first 2 are 0, 0. Now I know that the first one, this 0, must have been an A. All right, so this must be an A. That's good. Okay, now I've got this 0. So now I'm going to look at the next 0, the next position, and see a 0. So once again, by that same argument, this has to be an A, right? If it were part of a G, then this would be 0, 1. But because this is 0, 0, this must be an A. So let's do that next. Okay, I've got 0, and this time it's followed by a 1. So this 0, if I encounter this, looking at this 0, I could say, well, that could be an A, or it could be the beginning of a G. Now that I look at the next character and I see that it's a 1, well, I'm actually confused, right? Because it could be that the solution for these 3 characters here, is, for example, we could say it's A, C, C. Or we could say that the solution for those 3 characters there is G, C. It could go either way. There's nothing to break the tie. So we don't know we don't know exactly what's going on here. We have an ambiguous situation. All right, and what this speaks to is that condition we were saying before, that the function C is injective, right? That each symbol gets a distinct code. That's not enough. What we really need is for the concatenation of all the codes that we get to be unambiguous, in the sense that we can get back the original string. So we need a sort of higher level notion of what's injective. What we need to be injective is C. Let's define a new function C prime. C prime is just the code but extended, right? So it's the code applied to the entire input string, and where the output of the function C prime is the entire concatenated sequence of codes. Okay, so C prime, let C prime be the code C, but extended to sequences. So now C prime is a function that goes from sigma star, so any number of input symbols, to 0, 1 star. All right, any number of zeros and ones concatenated. This is now the concatenation of all the codes. Okay, and so if you give me a function C, it may or may not be the case that C might be injective, but it may or may not be the case that C prime is injective. So as an example, if this is our C, this is the example, the first proposal I showed before, then some examples of C prime, applying C prime would be, well, we can apply C prime to a single character, that's fine. And in this case, we'd get out 0. Right? It's only a single character. C prime applied to AG is the concatenation of the codes for A and G. So that would be 0, 1, 1, 0, A, G. Likewise, for TT, I've got 1, 1, 1, 1, 1, 1. And for AAAAC, I've got 0, 0, 0, 0, 1, 0. All right, you get the idea. So if C prime is injective, in other words, if every input string yields a distinct output string, output binary encoded string, then that's an unambiguous code. So C being injective was not enough. We needed C prime to be injective. Okay. So let's consider a couple of codes, both of which have this property. So here are 2 codes that are both unambiguous, A and B. And let's say I use code A to encode that first string, AAGC. What am I going to get? I'm going to get 1, 1, 0, 0, 1, 0. Okay? And let's say I use the other code now to encode that same string. I'm going to get 1, 1, 0, 0, 0, 1. So only slightly different. Okay? Now let's consider decoding. So let's take that encoding, the concatenation of all those codes, and let's work out what we would have to do to decode. Okay? Well, looking at that first one, right? There's 2 code words that start with that start with 1, A and C, and we don't know which one it is yet. So let's keep going. Can't tell yet. Okay. Now that I can see the first 2 characters, I can tell that first one must have been the code for A. So now I know I have an A, and the A is followed by, well, it could be an A or a C. I don't know yet. So I'm sure that the first one is an A here. I'm not so sure yet about this second one. It's either an A or it's part of a C. Keep going. All right. now that I can see 1, 1, 0, I still know that this first one is definitely an A, but it's not so clear what's happening next, because it could be that what I have here is 1 for, so let's write down these possibilities. One possibility is that I have 1 for A, 0, 0 for G. But another possibility is that I have 1, 0 for C, and then that this 0 is the beginning of another G. No, I'll write G partial, because I haven't got far enough yet to figure out if it's a whole G. So I still don't know what to put next, right? I still don't know what to put here. It's either an A or a C. I have to keep going to figure that out. Okay, so let's keep going. So now I get up to here, and I still have possibilities, because either I have A, C, G, and I haven't yet seen the second 0, or I have A, G. So I have to keep going. So I go to the next position. Okay, now now I know what I have. Now I know I have AAG. It's unambiguous now. I have AAG, and then I have a new code that starts with 1, so it's either AAG A or AAG C. So if I go one position further, now I know I have AAGC. So we made it. It's unambiguous, and we got a decoding of the original string. But what was interesting is that there was an ambiguity that actually lasted for a little while in the middle there. And now we can magnify that with an example that has a longer stretch of zeros in the middle. So now this example has a long stretch of zeros, and the point is that for this one here is we're gonna be in limbo that whole time, where we don't know whether that 1 is an A followed by a run of G's, or whether that 1, 0 is a C followed by a run of G's. We won't know until we get all the way to the end of the run of zeros, and we can know whether the run of zeros has even length or odd length. That's what's going to tell us, right? So if the run of zeros has even length, then it's an A followed by a bunch of G's. If the run of zeros has odd length, then it's a C followed by a bunch of G's, right? Right? So this makes this code not so desirable, because, you can imagine that in theory, this is a message that's being communicated to us. It's and the message might be interrupted in the middle, right? The message might be truncated. And if this particular run of zeros was truncated, that would mean that the damage extended all the way back to here. We wouldn't be able to figure out what the message was starting here. And similarly, if we're actually in the process of decoding this message, our decoder is going to have to sort of have a lot of deferred decisions, right? It's going along, and it can't make an instantaneous decision about what is the decoding for this part of the string. It has to wait until it gets farther along. And in this example, basically, that run of zeros in the middle could be getting longer and longer and longer, and that's longer and longer and longer we have to defer the decision about whether we're seeing an A or a C. Okay? So now let's switch back to code B and go through the same exercise. So let's go through our decoding exercise. So I see that first one. Now this time there's only one code that starts with 1, the code for A, which equals 1. So we know that that's an A there, no question. Immediately sure that it's an A. All right, now we keep going. We see another one. Again, we're immediately sure that it's an A. There's no ambiguity, because the only code that starts with 1 is the code for A. So so far, definitely we have AA. Okay, now we bring that 0 in. That 0 could be the beginning of a C or the beginning of a G. We don't know yet. So we keep going. Okay, yep, now we know it's definitely a G. So we have AAG so far. Great. Keep going. We bring in another 0. Again, could be part of a C, could be part of a G. Keep going. Now we can see it's definitely part of a C. No ambiguity. There was nothing like that situation we had before where some decision had to be deferred until later, right? We could pump in a bunch more zeros in the middle of this example, all right? and it wouldn't affect our ability to instantaneously decode as we go along. That's because this code, code B, has a property that's known as prefix free. Right? So none of these codes, 1, 0, 1, 0, 0, is a prefix of another. 1 is not a prefix of 0, 1. 1 is not a prefix of 0, 0. 0, 1 is not a prefix of 0, 0. And the other way, right? 0, 0 is not a prefix of 1, 0, 0 is not a prefix of 0, 1. No code is a prefix of another code. So a code that has this property is called prefix free, or sometimes it's just for short, it's just called a prefix code. The other code, if you'll recall, let's just write it down again. The code was A gets 1, and then C, we flipped it. C gets 1, 0, and then G gets 0, 0. Was this prefix free? No, because the code for A was a prefix of the code for B. So that was not prefix free. Another term for prefix codes are instantaneous codes. I was already using the word instantaneous, right? Because as you go along, you don't have to defer the decoding decisions. You can make them instantaneously. As soon as you get to the full length of the code for the character you're trying to decode, you know unambiguously what that original character was. How do we build an unambiguous prefix code? This seems to be a very nice kind of code. Is there going to be a really complicated and hard to understand algorithm for building prefix codes? Well, no. There's a very easy algorithm, which is called Huffman. We build something called a Huffman tree, and the Huffman tree gives us the code, and that code will be an unambiguous prefix code. Okay. So let's go through an example to see how Huffman works. So let's say we start with a string, abracadabra, and we're first going to count up how many times each symbol occurs in that string. So we've got 5 A's, 2 B's, 1 C, 1 D, 2 R's. And then we're going to take each of these characters and their frequency and create the beginning of what's going to end up being a tree. But right now I'm drawing the leaf nodes of the tree. So I'm drawing 5 nodes, not connected to each other. They're labeled with the character, but they're also labeled in kind of a superscript with the number of times that that character occurs. It's kind of like a weight for that node. And we're going to proceed in several rounds. And in each round, we're going to join the 2 subtrees that have the lowest total weight. Right? So we're going to find, of all pairs of subtrees that already exist, I'm going to find the 2 that add to the lowest weight, and I'm going to join them. And the way I'll join them is I'll draw a new parent node, and then connect the 2 subtrees' parent nodes as children of the new parent node. Now I'm talking about subtrees. Right now we don't have, all we have are these disconnected leaf nodes. But as we iterate, we will be building larger and larger subtrees. So let's do the first iteration. No surprise here, right? I've got 2 nodes, both with weight 1. So those are the 2 that I'm going to join in the first round. When I join them, the new subtree will have weight 2. So how do I join them? Well, I just draw a new parent node. It's going to be connected to those. It's going to have the weight 2. Okay? All right, the weight of the new subtree is the sum of the children. And I'm going to keep going. Now I need to pick the pair of subtrees with the lowest total weight. There's a tie now, actually a 3-way tie. So I have 3 different ways of picking 2 subtrees that have weight 2, and therefore that will add to weight 4, which is less than weight 5. So I just break the tie arbitrarily. So in this example, I'll join these 2, the subtree I already built, and then the leaf node for B. And now I have a new subtree that has weight 4. Okay, now I'm going to go into the next round. Okay, I've got a subtrees of weight 5, 4, and 2. So the subtrees of weights 4 and 2 are going to get joined next. And now there's only 2 subtrees left, so the only thing I can possibly do is join them. And here we go. I have a Huffman tree. This is the result of going through that Huffman procedure. So that's the tree. What's the code? Well, the code comes from adding some labels to this tree. So we're actually going to label the edges with 0 or 1 according to whether the edge is coming down as the left or the right child of the parent. Right? So let's start at the root. Here's the edge that goes to its left child. I'm going to let all the left child edges get 0 as their label. Okay, and so this is my right child. That's going to get labeled 1. Keep going. Okay, let's say we're at this node. Here's its left child edge, so that's going to get labeled 0. All right, and so on. All the left child edges get 0. All the right child edges get 1. And so now if we want to know the code for a particular character, we walk down from the root to that character and call off, just sort of read off the edge labels as we go down. So for example, let's write in some of the codes. The code for A, let's see, that's just going to be 0. Nice and simple. All right, the code for B is going to be 1, 0, 0. Okay, the code for C is going to be 1, 0, 1, 0. 1, 0, 1, 0. The code for D is going to be 1, 0, 1, 1. The code for R is going to be 1, 1. Okay, those are my codes. Is this a prefix code? Let's check. Okay, I've got 0. 0 prefix of any other code? No, 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 no. All right. Let's go to the next longest code down here, the code for R, 1, 1. Is 1, 1 a prefix of any other code? No, 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 no. Okay, let's go to the next longest code, the code for B is 1, 0, 0. Is that a prefix of any other code? No, no. Obviously, you can finish it. None of these is a prefix of any of the others, so I definitely have a prefix code, which we also call an instantaneous code. Huffman codes have another nice property. They are optimal in a certain sense. So Huffman codes are optimal in that each code, each code corresponding to a symbol, each code is at most 1 bit longer than optimal, than the code that would optimize to the zero order empirical entropy. So in other words, we can write down a little equation. For an input string S, the length of the bit vector that we get applying our code, if it's a Huffman code, will take at most a number of bits equal to the length of the string times the zero order empirical entropy of the string plus 1. Okay, so this is optimal, and then this is up to 1 bit of waste per symbol. All right, and then this is multiplying by the number of symbols. Okay. So there we go. The Huffman codes are optimal in this sense. And there are other coding schemes that are optimal in different senses. So arithmetic coding, for example, achieves, in some sense, an even more optimal scheme because the number of wasted bits is not per symbol, it's just overall for the entire sequence. So that 1 that's inside the parentheses here, you can imagine that sort of comes outside the parentheses and gives an even better result for how many wasted bits there are. We won't cover arithmetic coding here, but that's also a wonderful topic. And we'll stop here.